All right, guys, Audrey here. So today we're going to do a L'Hopital's rule question that gives the case of 1 to the power of infinity. Notice that, remember that the technique we use with the power 1 to the power of infinity is the same to the technique that we would use for 0 to the power of 0 or infinity to the power of 0. All of these are indeterminate forms that result in the same technique. So let's start off by plugging in. When I plug in my infinity here, I get infinity over infinity to the power of infinity. Now, remember that that infinity over infinity is in and of itself an indeterminate form. So I'm going to take the thing that causes infinity over infinity and evaluate that off to the side. So the limit as x approaches infinity of x plus 4 over x minus 8. Here we're approaching infinity. We've got a polynomial over a polynomial. We can just take the big stuff and see immediately that this equals to 1. So what we actually have going on here is 1 to the power of infinity. So that is an indeterminate form. And with this indeterminate form, the technique that we use is e to the power of ln of all of this stuff. So we're going to remember that e to the natural log of f of x is just equal to f of x. So we're going to rewrite our function in the form e to the ln of the function. But when we do that, we're going to leave that e on the outside of the limit. So the limit as x approaches infinity of natural log of x plus 4 over x minus 8 to the power of 4x minus 1. And that 4x minus 1, that looks like plus 1, that 4x minus 1, using our log rules, can now be brought down to the front. So this equals to e to the limit as x approaches infinity of 4x minus 1 natural log of x plus 4 over x minus 8. So now I'll plug in again. And when I plug in again, I end up with infinity ln. I already did that inside bit. That x plus 4 over x minus 8, I know is going to 1. And ln of 1 is 0. So this is infinity times 0. So now I'm going to remember that e right there. I'm going to put a big star by it so that I don't forget to go back and use it. And I'm just going to ignore it until the very end. So now this gives me the limit as x approaches infinity. I need to decide which one of those things I want to bring to the denominator. Infinity times 0, we want to turn that into 0 over 0 or infinity over infinity. So do I want to bring 4x minus 1 to the bottom or ln of x plus 4 over x minus 8? Bringing 4x minus 1 to the bottom is going to result in things that are easier to differentiate. So we'll have ln of x plus 4 over x minus 8 all over 1 over 4x minus 1. Now, when I plug in, I get ln 1, which I know is 0, 1 over infinity, which is also 0. I end up with 0 over 0. And so I can use L'Hopital's rule, but it will probably be easier to take the derivative of the numerator if I separate it using my log rule. In other words, if I say this is equivalent to the limit as x approaches infinity of ln of x plus 4 minus ln of x minus 8 over 1 over 4x minus 1. Now this is still 0 over 0. You might think, oh, but hey, ln of infinity is infinity. So isn't that numerator giving me infinity minus infinity now? And the answer is yes. But the answer is also that in this case, that infinity minus infinity is 0, because ln of x plus 4 minus ln of x minus 8 is the same thing as ln of x plus 4 over x minus 8, which we already know to be 0. So of course, this difference will also have to be 0. So I'm going to think of it like that, and I'm going to do L'Hopital's rule from here to give me the limit as x approaches infinity, 1 over x plus 4 minus 1 over x minus 8 over negative 4 over 4x minus 1 squared. That negative 4 coming from the chain rule that I did when I did the derivative of 1 over 4x minus 1. 4 is the derivative of 4x minus 1. Now, remember, before we apply L'Hopital's rule, before we do anything, we want to simplify as much as possible. So I'm going to multiply the numerator and the denominator by 4x minus 1 squared. And I'm going to take that negative 4 there and move it outside the limit. So this is negative 1/4. The limit, as x goes to infinity, 4x minus 1 squared over x plus 4 minus 4x minus 1 squared over x minus 8. Now, I could do this. I don't have to. What's left in the denominator? The 4x minus 1 squareds cancel out. That negative 4 I already brought to the outside. All that's left in the denominator here is a 1. So really, I don't even technically have to write it. I'm going to erase it. It doesn't have to be there. Okay, so now, before I keep going, before I even plug in again, I see that this is kind of gross. I've got x's in the top, x's in the bottom, plus a difference. So I'm going to now combine these things as much as possible. I see that there is a greatest common factor of 4x minus 1 squared. So I'm going to factor that thing out. I could have just left it factored out to begin with. So I'm going to have 4x minus 1 squared times 1 over x plus 4 minus 1 over x minus 8. And now I'm going to combine that fraction to give me the limit as x approaches infinity of 4x minus 1 squared times x minus 8 minus x minus 4 over x plus 4 times x minus 8. So I just found my common denominator. Now those x's cancel out. Minus 8 minus 4 is minus 12. Don't want to forget this negative 1/4. That should be going in front of the limits here. So I'm going to take this negative 12 right here and bring it out on top of the 4. So I end up with negative 12 over negative 4, the limit as x approaches infinity of 4x minus 1 squared over, that's kind of ugly, 4x minus 1 squared over x plus 4 times x minus 8. So let's go back to the previous slide just to make sure that you guys see that. So we have the 4x minus 1 squared. What's left in the numerator, that minus 12, got moved to the outside, so there's just a 1. And then we have x plus 4 times x minus 8. I put them all under 4x minus 1 squared. Perfect. Okay, so now I have a polynomial over a polynomial. I have infinity over infinity in the form of a polynomial over a polynomial. I'm approaching infinity, which means, sure, I can use L'Hopital's rule, but I can also just take the big stuff. So I'm just going to take the big stuff. That's going to have me an x squared on the bottom. It's going to give me a 4x squared on the top. So negative 12 over negative 4, that's 3. The limit as x approaches infinity of 4x squared over x times x. 3, the limit as x approaches infinity, 16x squared over x squared. The x squares cancel out, giving me 3 times 16, which is 48. Now that 48 right there is not the final answer, because remember, in the beginning, we had this e right here that we have starred and circled that we don't want to forget, so let's not forget it. Back to the next slide. So that means my final answer is e to the power of 48. Now, that's one way to do this problem. There is actually another way that I could have thought about this problem. So we're going to do this problem one more time using a completely different method, but that ultimately comes to the same thing. So the limit in question here was, the limit as x approaches infinity of x plus 4 over x minus 8 to the 4x minus 1. So the first thing that I'm going to do here is use my special division technique to make the numerator look like the denominator. So I'm going to do minus 8, and then I'm going to do plus 8. And that's going to give me the limit as x approaches infinity of x minus 8 plus 12 over x minus 8, all to the power of 4x minus 1. So here we're doing this in another way. Now, the reason that we applied the special division technique, same as what we would do before, is we're actually dividing this. So I'm dividing x plus 4 by x minus 8, and I'm going to end up with the limit as x approaches infinity of 1 plus 12 over x minus 8 to the 4x minus 1. Now, I'm going to remember my rules about exponents. 4x minus 1, I can separate that to give me the limit as x approaches infinity of 1 plus 12 over x minus 8 to the 4x times 1 plus 12 over x minus 8 to the negative 1. Now let's plug in. So when I plug into this part right here, I have 1 plus 12 over infinity, all to the power of infinity, which gives me 1 to the power of infinity. That's my indeterminate form. Here, I have 1 plus 12 over infinity to the power of negative 1. That gives me 1 to the negative 1, which is just equal to 1. So that's not an indeterminate form. It's actually not going to change my limit at all. What that means is I really just need to focus on this part right here. So we're going to take that part and separate it away and just look at that, giving me the limit as x approaches infinity of 1 plus 12 over x minus 8 to the 4x. That gave me my 1 to the infinity. So now we're going to do the Elon technique that we did when we did this problem the first time. So this is going to give me e to the limit as x approaches infinity of the natural log of all of this stuff. We can bring that 4x down. We're going to ignore the e until the end and end up with the limit as x approaches infinity of 4x times natural log of 1 plus 12 over x minus 8. Okay, so this is really the only limit that we actually need to calculate here. So let's go to the next page. The limit as x approaches infinity of 4x times natural log of 1 plus 12 over x minus 8. When I plug in now, I get infinity times ln 1, which is 0. So should I move the ln to the bottom or the x to the bottom? I'm going to move the x to the bottom. At the same time, I'm going to move that 4 to the outside of my limit. So now I have this, and now that gives me the form 0 over 0. So I'm going to use L'Hopital's rule and take the derivative of the top and the derivative of the bottom to get 4, the limit as x approaches infinity of 1 over 1 plus 12 over x minus 8. Using the chain rule, I'm going to multiply by negative 12 over x minus 8 squared, all divided by negative 1 over x squared. So now that negative 1 over x squared, I want to bring to the top. I'm going to cancel out my negatives here, so I'll make this a positive. That 12 I'm going to bring to the outside. So this gives me 48 times the limit as x approaches infinity of 1 over 1 plus 12 over x minus 8 times the 12 I brought to the outside, but I'm going to bring that x squared up, and I'm only going to give it to this part. So I don't need to distribute it to both parts. It's multiplication. I'm going to give it to this part and not the other part. X squared over x minus 8 squared. Well, actually, when I look at this, that gives me 1 over 1 plus 12 over infinity which gives me 1 over 1, which gives me a 1. So that part's just 1. And when I look at this part, I can actually just take the big stuff. So I get x squared over x squared, which is also equal to 1. So I don't have to do L'Hopital's rule again. I ended up with something that's pretty straightforward. I thought of it as 2 separate parts, and remember that is an incredibly useful technique when we're evaluating complicated limits like this. Separated into parts that are both manageable. We got a 1 times a 1. So this is 48 times 1 times 1, which is equal to 48. Now, if we go back to the previous page, what that means is here, this part was equal to 48. That second part was 1, and we get that the answer here is, oh, I'm sorry, 48. Don't forget the E. For a final answer of e to the power of 48. So it's easy to forget that e. Make sure that you don't go back and forget it. That's it. We're done. So that one should actually probably be more like this. And there are 2 different ways that you could approach this problem. The second method is incredibly useful for something that we're going to do soon in one of the next topics in the class. So it is useful to get comfortable with using that special division in the context of limits as well. All right, that's all, guys. Bye.